Okay, we can start. Just a couple announcements. Okay, so when's our homework due? Tomorrow at the beginning of class. Now, just so you know, if you've been watching the weather, there is a storm coming. Hopefully I can get out. My wife and I, we live out in the middle of the woods. We have a ridiculously long driveway. We didn't build it. It's just the house that we purchased. Frequently, I can't get out of the driveway when there's a big storm. So there's a chance, and I'm surrounded by Mennonites. And so the infrastructure, when you're surrounded by Mennonites, technological structure, internet is remarkably bad. And so there's a chance that I can't come in, and then because of the internet that we have at home, which is pathetic, I don't even know if I can do classes. So I just don't know what it'll be. So if it looks like I can't get here, I'll send you an email to say that I can't get here. And then what we'll do, the homework will then be due on Wednesday. Okay? Questions? Okay, we also have a test coming up. Test 1. And it'll be Thursday evening on next week. So it'll be Thursday evening. Next week. Okay. And it'll be here. The reason I like to do this is I really hate having time pressure on exams. Usually it took me a half hour to figure out where to put my name, and after I put my name, I didn't have any time to do anything else. So I'll give you as much time as you need within reason. Now there's a couple little caveats here. Okay, here's the caveat. Is if we're in this room for over 2 hours, if somebody comes down with COVID, then basically the entire group gets quarantined. And so to help avoid that, I'm going to split the test up into 2 pieces. This will be part 1 of the exam. And then on Friday the next day, in class, we'll have part 2. So part 2 of the exam will be Friday in class. Like that. The way I do the test is on part 1. Part 1, there's going to be 6 questions. And these will be short. Okay, I'm not going to give you any plug and chug. So if you think I'm going to give you a plug and chug problem, there's not going to be any plug and chug. But these will be short problems, just kind of like one part here. What I expect you to do is I want you to do 5 of the 6 questions. You don't have to do all 6. Only do 5 of the 6. Do any 5. If you want, you can do the 6 as a bonus question. And I don't care which one it is. So maybe you answer is 1, 3, 4, 5, and 6. Maybe you don't answer question number 2. In your case, number 2 will then be the bonus if you choose to do it. Now here's just some test strategy. If somebody's giving you a bonus question, what do? You try it. Even if you have no clue what you do, I do get partial credit. Try it. Just don't leave it blank. That's just being silly. Don't do that. Okay? So that'll be part 1. Part 2, which will be in class the next day. These will be, so for part 2, these will be 3 longer questions. And you're going to do all 3. Okay? And what I do to kind of help people out, I actually always hand out the previous year's test. So I'll make photocopies of the exam I gave last time I taught this course. I'll hand them out to you, and then that'll give you some practice of what I expect you to be able to do. Okay? But I've already promised you one thing. What did I promise you? Promised you on Friday it would be on this test. I'm going to give you a case where I give you 2 vectors, and those vectors are going to be in 3 dimensions. You know, I'm going to give you the length of the vector and those 2 angles, like we did on Friday. I'm going to have you calculate those components, and then take the dot product between those vectors, and then find the angle. So I've already told you what one question is. Okay? Questions? That would be a long one. Yeah. That would not be a short one, because there's a lot of oomph there. Yes? No. But there will be fill in the blank and there will be a connect the dots. Okay? Then I'll have you also trace out your hand and draw like a little picture in there. And then I'll have you write a little poem. If you could be an equation, which equation would you be and why? And also, what's your favorite equation? You'll see what it's like when I hand out the thing. Questions? Okay. Now, for lab today, you're going to be doing projectile motion, and we're going to start that. In principle, we'll be starting it tomorrow. So what I'm going to have you do, I want to do an example of those 3D problems I talked about. But since some of you have lab today with the projectile motion, what I want you to do is in your notes, skip about a page, meaning the front of a page and the back of a page. Skip a front and a back page. We're going to come back to it. I'm going to give you an example of what I expect you to be able to do on the test. But what I want to do now is talk about projectile motion to get you ready for the lab today. So skip the front and back of one page. Okay? We're going to come back here because I'm going to give you an example of what we did on Friday so you can see. But right now what I want you to do, we're going to start another topic, and this will be the last stuff on the test, and it's projectile motion. And the nice thing about it, to be honest, there's nothing new. You actually know all the stuff, all the equations. We just have to apply them in 2 dimensions. And so in some sense, we get a lot of mileage for no extra work. So let's see what we can do here. So the next topic is going to be 2D motion. So we've been doing 1D motion, and 1D motion, what did we do? We had motion this way, or we had motion this way, or maybe up an inclined plane. What we're going to do now is we're going to start throwing things. So if I throw this, what's it going to do? It's going to go like this through the air. It's going to have some sort of motion in the X motion and in the Y motion. So we have to account for both motions. So this is going to be Y here. This will be X here. And so maybe we're going to throw something like this, and it's going to go like this. And we want to figure out how this motion is going to go. So I want to set this up, and what it's going to turn out is that when we do the case of constant acceleration, it turns out we have those equations. There's nothing new to learn for this. So let's set this up and see how it goes. So let's consider a general motion in 2D. So here's some Y, and here's some X. And I'm just going to draw something like this. Doesn't matter what it is. And this is going to be my initial, this will be T1. And this will be sometime T2. Now what we're going to do, we're going to let R be the position vector. From the origin. So I'm going to say from the origin to this point here, I'll call that R1. So that's the position vector at time T1. And then the position vector for this guy over here, that is R2. Okay? Now, how could you write a position vector? So how can you write it in a vector? I can always write it in terms of an X and Y component. So I can drop a little perpendicular here like this. I'll call this X1. I'll call this distance here Y1. So how would I write the position vector at R1? If I give you the X1 component and the Y1 component, write that for me in terms of a vector. Write it in terms of unit vector notation. How would you write that? Okay, so tell me what to write. So I want to take this vector here. So if its length is x1, and if it's pointing in the x direction, how do I write this vector here then? How do I write a vector going this way with the length of x1? x1 I hat. So all this is here, this is just this vector here. That's what that vector is here. Now what I want to do is add this vector here. So how do I write that vector? This would be plus y1, j. I'm going to write that a little bit bigger. So this would be x1 I hat plus y1 j hat. So this guy here is this guy. We're going to add it to this guy here. And this vector plus this vector equals this vector here. Does that make sense? Hey, let's figure out how we can write that crazy R2 vector. So how am I going to write this R2 vector? Well, again, I'm going to drop my little perpendicular. So this is x2. This is y2. Now tell me how to write then R2. Yes. Well, x2. x2 I hat plus y2 j hat. Because it's going to be this vector here going this way. Then we're going to add to it then this vector here, because this vector plus this vector, tip to tail makes that vector there. Does that make sense? Now, I want the difference between the two. I want this vector here, which I'm going to call delta r. So delta r is going to be the vector going from here to there. What would that delta r have to be? So let me kind of try to take out some of the lines here to make it a little bit easier to see what's going on here. Here's my R1. Here's my R2. I'm saying that this vector here is delta r. So I'm saying this vector, R2, or R1, plus this vector here, delta r. This vector plus this vector has to equal this vector, R2. So what is delta r? Delta r is the R2 vector minus the R1 vector. It looks just like the final minus initial value we had before. So you're going to say delta r is in R2 minus R1. Right, it's just the difference between these two vectors, is that guy. Which is going to be what? My friend x2 is, my friend R2 is x2 I hat plus y2 j hat. That's this fellow. Minus this one over here, x1 I hat plus y1 j hat. That looks kind of messy. What would I do with that? Yeah, let's put all the I hats together and all the j hats together. So this is x2 minus x1 I hat. I've grouped this one and this one together. And then I'm going to group this one and this one together. And that is my delta r. But hey, what is this? Do we have another name for this guy? Do we have another name for that guy? They're delta x and they're delta y. So this is delta x, and this is delta y. So my delta r is what? It's delta x I hat plus delta y j hat. Hey, I might want the average velocity to go from here to there. How do you think I'm going to define the average velocity? Think about what we did in one dimension. Yes. Oh, okay. Yeah. Say a little bit more about the time, and you're right. Delta time, over the change in time. So if I want the average velocity of this, I'm going to take the distance this thing moved. It moved this distance here. Okay, I'm going to divide it by the time it takes to go from here to there, which is my delta t, which is t2 minus t1. So I'm going to say the average velocity here. I just put an AVJ there for average, AVG. Is going to be by definition delta R over delta T. If I put this in here, what do I get? Okay, in the end, we're going to end up with something that's going to be straightforward. So all I did was I took my friend delta R and put it up into here. And I divided both sides by delta T. Oh, hey, we have new names here. Does this have a name? Not yet. Hold off on that. Hold off on that thought. In which direction? In the x direction. So this is the average velocity in the x direction. Remember we put a bar over something? So that's your average velocity in the x direction. Hey, then what's this going to be? Average velocity in y. And so we get something that's not too surprising. But if I want the average velocity of this guy here, if you're wondering why I didn't put a bar over this one, but I'm putting bars over here, it's because if I have this vector symbol here and then put a bar over it, it's starting to look a little funny. That's the only reason why I'm not doing that. So this is going to be the average velocity in the x direction plus the average velocity in the y direction. So this and this are the same thing. But hey, I might want to know the actual velocity at this point here. What would you then do? What? I want the actual velocity at this point here. I don't want the average velocity between these 2 points. I want to know exactly how fast that object's going there. Yeah, what's that called? When you move the points closer together. What did mathematicians say? You would take with a limit, which is going to lead to the derivative. So if I want the actual velocity at this point, if this is t1, if this is t2, I'm going to let that delta t between those 2 times become smaller and smaller and smaller and smaller and smaller. And that will be the actual velocity at that point. So what I'm going to say is that the actual velocity at this point is going to be the limit as delta t goes to 0 of my friend here, delta r over delta t. And it's going to give a result that's not too surprising. So this will be what? This will be the limit as delta t goes to 0. I'm going to put in my friend here. Of that. Well, hey, if I take the limit as delta x over delta t goes to 0 here, what does that become then? That's the definition of the derivative with respect to x. So then this guy becomes dx dt I hat. That's what this one becomes. Hey, but if I take now delta y over delta t and take the limit as delta t goes to 0, what does that become? That becomes dy dt. Well, we have another way of writing this. Dx dt, what's another name for that? This is a friend. The x velocity. The actual velocity here, I hat. And then this guy becomes the y velocity. Here. Where Vx is gx dt, and Vy equals dy dt. So all we do is extend this like you would naturally think. If we had 3 dimensions, what do you think would happen? We're not going to do 3 dimensions, but if we had 3 dimensions, what would happen? Yeah, you'd have a plus Vz k hat, and Vz would be dz dt. You can, and that occurs in special relativity and general relativity. You have 4 dimensions. The 4th being the time. And then when you do general relativity, it gets more messed up because you're dealing with a curved space. And so you have to redefine what you mean by all the derivatives, because the derivatives are in a curved space and they get really screwed up really fast. If you're really interested in that, you take my course in general relativity that I'm teaching now. I will teach you how to do that. It actually is cool. So in the only classes where you actually legitimately talk about time travel in a legitimate context. Questions? Okay. Now, one more graphical thing, and then I want to show you what you can do with this. So graphically, V is tangent to the y versus x graph. Okay. So graphically, this is what you'd see. So we'd have here, here's x, here's y, here's our little path like this. If I want the velocity at this point here, it's actually going to be tangent to that right there. That would be the velocity right there. If I'm right here, the velocity would be tangent here. If I'm right here, the velocity would be tangent to that line there. And you can see that for the following reason. That if here's your, oh, that's a little too steep. Okay, if here's your R1, and if here's your R2 like this, and if here's your delta R, you can see if you make this point get closer and closer and closer and closer to here, this delta R is going to be tangent to that path here, and that's why. So as delta T goes to 0, delta R becomes tangent to the y versus x graph. Okay, one more thing, and then we have all the theory. It's actually quite slick. You tell me how we're going to find the acceleration. I'll give you a hint, you're pros at this. If I were to now say derive the acceleration equation, you would know exactly what to do. You tell me what to do. With respect to? Done. This is going to be nothing but dv dt, using the exact same argument as before. There's no variation in this. So what is this? My v is my friend, vxi hat, plus vyj hat. Well, what is this? This is dvx dt, I hat, plus dvy dt, j hat. Hey, you tell me what dvx dt is. And everyone knows it. This is my friend. No. AX. This is my friend. AY. So we had this. Okay, we're done. The theory is now complete. There's no more theory to learn. We're just going to take a special case. So let's look at what do you think that special case is going to be? Okay, we're going to look at that one, but not today, because I want to get you ready for lab. What do you think what was the special case when we had the 1D motion? When we did the 1D motion, the special case, yes. Exactly. So now let's look at constant acceleration. Okay. So the special case of constant A. If A is constant, what does that mean? It means that AX is a constant and AY is a constant. So what are you going to have in the X direction and what are you going to have in the Y direction? No. Oh, true, yes. What else do you think will be true with these? When we did the 1D motion, what did we know about constant acceleration? What did we always find out? That's a special case of constant acceleration. When the acceleration is constant, what's always true? Those, how many? Those three equations are always true. And you can have the exact same thing here, but how many equations are you going to have now? 6. You can have 3 for this motion, and then 3 for this motion. So those 3 equations are separate here. Those 3 equations are separate here. Okay? They would be given, but so I'll give you the equations on any of the exams, but you have to know what to do with an equation sheet. In other words, if you read a problem and go, wow, I have no clue what to do, I'm going to look at the equation and find out variables that match what is given, and I'll solve for the remaining thing. Okay, you're dead. You're not, it doesn't matter whether the equations are there or not, you are dead in the water. Because what it shows is that you haven't spent enough time really doing the homework and thinking through the problems. What you want to do is like, oh, I know how to do this, but okay, does that equation have a half in it? Oh, let me look. Oh yeah, that equation has a half in it. Oh, that's right. That's how you use an equation sheet. If you're looking for an equation sheet to basically help you figure out how to do these things, it's not going to work. It's going to actually be really, really bad. So you have to know how to use an equation sheet. Okay? Questions? So let's write this down and actually do something. So if AX and AY are constant, those 3 equations are valid in both the X and Y directions. So let's see how this works. So when you do this at t equals 0, we have some initial velocity called v naught. The initial velocity is going to be the initial velocity in the x direction I hat plus the initial velocity in the y direction j hat. What else will we have? We'll have the initial position. So the initial position will be r naught. How will I write r naught? Well, x naught I hat plus y naught j hat. So what's going to happen here? What do you think you're going to have in the x direction? Okay, what did we have in one direction, in one dimension? We had x naught plus v naught t plus 1/2 a t squared. Now put it in our fancy language over here. We're going to have x equals x naught plus, it's not going to be v naught, but it's going to be v naught x t. So it's going to be the initial velocity in the x direction plus one half ax t squared. What do you think the y equation is going to be? Why not plus v naught y t plus 1/2 ay t squared. Okay, so that's a position equation. What were the other equations we had? Guess what it's going to be for this one? So remember, we had 3 equations. We had the position one. What else did we have? The velocity one. So what is it going to be in this case? It won't be v, it's going to be vx. So this will be vx equals v naught x plus axt. And you can see that if I differentiate this with respect to time, I get exactly this equation here. Hey, tell me about the y equation. What would the y equation be? Yes. Well, we had 3 equations. What was the third one? V squared. So this is going to be v x squared equals v naught x squared. Okay, 2, tell me more about ax, then what, delta x. Hey, but we have a y equation too. What do we have in the y equation? Yes. The reason I didn't derive these is the exact same derivation that we had in one dimension. There is no variation in the derivation. They're identical. And also, I want to get to a free fall problem. Okay, does that make sense? Again, when can you do that? Only when the acceleration is constant. If it wasn't constant, what would you have to do? Never a bad thing to do. Okay, good. Okay. How did we do it when I gave you non-constant acceleration before? Which you're going to be getting on the exam too. I don't think that's any surprise. You'd say like a equals dv dt, then you'd integrate it out. You'd have to do the same thing with these. Okay? And I'm going to give you some examples, but after we do of something like this. Okay, let's take a very special case of free fall. So let's look at free fall in 2 dimensions. If you say free fall in 2 dimensions, that has a better name to it. What's a more common name for free fall in 2 dimensions? Projectile motion. This is, projectile motion. That's what we mean. Okay? So let's figure this out. If we what does it mean to be free fall again? Well, the only thing acting on you is the gravitational attraction of the Earth. In other words, your weight or the gravitational attraction of the Earth pulling you down. Which way does that act in? Only in the y direction. Okay, it only pulls you down. So if I had to write something like this, if I had to write axi hat plus ayj hat, what would this become? In free fall, what is my x acceleration? It's 0. So this is 0 I hat. What is my acceleration in the y direction for free fall? Okay, the minus 9.8, but I'm going to write the 9.8 as g, so this would be minus g, j hat. Okay? There, let's do a problem. We've mastered all the, we have all the pieces. Let's take an example. So let's say, okay, we're going to take a rock, and we're going to throw a rock like this. Now let's say we're going to throw a rock this way at 10 meters a second. And we're going to throw that rock at a 30-degree angle. And we need a height for the building. Let's say this building is 20 meters. Okay, what is that rock going to do? That rock's going to do this. No. Like that. What might you want to find out about that rock? Okay, time to reach the max height. What else? When it hits the ground, what else? Yeah, how fast is it going before it hits the ground? What else? Okay, what else? Okay, that's given. You're missing the obvious one. We're going to calculate that one. Yeah, how far does it go? You know, what is this right here? Find how far it went from the base. We give that a name. We call that the range. Okay? Let's go through and do this. Okay, so if you had a problem like this, what would you immediately do? So go through the reasoning process. So if you see a problem like this, always classify your physics problems. So you see something like this, and what would you say about this problem? What kind of problem is it? A projectile motion. And what does projectile mean? It means free fall. Okay? So what does free fall mean? Yes, it means that your AY is your minus 9 point, is your minus G. Your AX is 0. And you would say, oh, I know about these. What are these? These are, a mathematician would classify this as constant. These are constant accelerations. As soon as you know constant acceleration, what else do you have to know? Those three equations have to be valid in the x direction and valid in the y direction. Now, it turns out when you do these, you're going to get a little more mileage in the y direction typically, but not always. So for part A of this, let's find how long it takes for this to hit the ground. So for part A, how long does it take for the rock to hit the ground? Okay, proceed. You tell me what to do. You are pros at this. Okay, so let's find the initial x and y components of the initial velocity. So first of all, when you do this, you need an origin. Okay, there's only two good places to take your origin. Where would they be? Here or down here. You can take any origin you want. Like I say, I'm going to take this to be my origin. That's stupid, but it's not wrong. Okay, so I take down here and take up here. I'm going to take down here for no good reason. So here's this is my origin right here. That's my origin. So let's figure this out. Let's figure out x naught and y naught and v naught x and v naught y. Let's get those first. What is my initial x position for this? 0, right? If I look along the x-axis here, because here's my origin, this is at 0. What's my initial y position? Yeah, if I'm measuring this way here, it's starting here, so this is going to be 20. If I picked here to be my origin, what would be my initial y? It would be 0, exactly. Now let's figure out how to do v naught x and v naught y. So let's draw this picture out. Here's, when you do these, always draw this out too. So here's my v naught magnitude. Here's my v naught x. And here's my v naught y. And this is theta. If I want v naught x, what am I going to do? Done. Which part of the triangle is it? The adjacent. So which one do we want? The cosine. So you're going to have cosine of theta equals the adjacent side, v naught x, over the hypotenuse, which is my friend here, magnitude of v. This tells me that v naught x equals the magnitude of v naught cosine of theta. So in this case, it's going to be 10 cosine of 30 degrees. What is cosine of 30 degrees? No. Square root of 3 over 2. Okay? So this is 5 square root of 3. Tell me how to find v naught y. Yes. So if I want this side over here, this is, again, if here's my triangle, this is the opposite side of my triangle. So I'm going to say sine of theta is my opposite over the hypotenuse. So my v naught y is over here. It's magnitude of v, sine of theta. So this is 10 sine of 30. Sine of 30 is half. So this is 5. Okay, so I have my initial stuff. Now ask yourself, which direction do we have a little bit more stuff in? Okay, I want to find the time it takes to go here. So do we have a little more information in the x direction or a little more information in the y direction? I don't know. Okay, so we have the initial x, initial v naught x. What do we have for, so 3 things we have for the x direction. What do we have for the y direction? V naught y, vy, ay. Well, we have one more thing. We know it starts here, but we also know, where does it end up? On the ground. We know the final position. So we have a little bit more y information. So we're going to go with the y information. Okay. So tell me what to write for the y direction then. Tell me how to find them the time to go here. What are you going to do? Okay. Which one? It's going to be the y. It's going to be y equals y naught plus v naught yt. Yes, and so let's figure this out. Where does the rock end up? It ends up here. What is my y value here? Now this is y equals 0. It's on the ground. So this is 0. Where does my rock start? It starts at 20. Plus, what is my v naught y? Does it have any initial velocity in the y direction? If it had 0, how would you be throwing the rock? I'd be throwing it like this. It'd be going straight like this. Okay? But this is, I'm tossing it like that. So it has a certain y velocity right here. And that's equal to this 5 here. So this is 5t plus 1/2. What is my ay? Friend, minus 9.8 times t squared. This is our friend. Which friend is this? What? This is a friend. Quadratic equation. So t equals, you tell me what t equals. Minus b, which is minus 5. Keep going. Plus or minus square root of 5 squared minus 4 times. Yeah, this right here is minus 4.9 times 20. Okay. Yeah, all over 2 times, here's my value, a, which is going to be, I'll write it like this. Right, this right here is my minus 4.9. And you get this. Which time do we keep? The positive time. I want to say one more thing now, assuming I have time. I do have a little. Has somebody worked this out? Are we going to keep the positive sign or the minus sign? Why the minus sign? Yeah, the bottom, no matter what, is going to be what? Negative. So that top, this whole top here has to be negative as well. Okay? And so with the minus and the minus, that'll make a negative, which will cancel then the negative down there. So can somebody work that out and tell me what you get? .6. So that's how long it takes to hit the ground. Now for part B, let me do this part here, then we'll call it good for the day. I want you to find the range. So again, what is the range? Range is when we toss it like this, it's going to go like this. The range is how far it goes along the x-axis here, and here's our origin. You tell me what to do. Okay, in which direction? X. So let's do this. So we're going to have x equals what? X naught v naught x t plus 1/2 ax t squared. Okay, let's see what we get for this. What is x naught? 0. What is v naught x? 5 times square root of 3. What time is it? I mean in the problem. In the problem. 2.6. Okay. Plus 1/2. What is the acceleration for free fall in the x direction? It's going to be 0. The 9.8 is in the y direction. So this is 0 times t squared. Okay? That's 0. This is 0. So we're left with x equals, can somebody work that out for me? 22.5 meters. Okay? So that's how far it gets from the base. That'll put you in good shape for the lab. Okay? So homework is due at the beginning of class tomorrow, unless I can't come or there's a snow day. Both of which are, I think, possible. Have a fantastic day. Thank you.